usually the only Eduardo around, but it's different here. Okay. So we're going to have 2 exciting weeks. This week there will be a number of lecture-type presentations with the goal of actually bridging the gaps between, we have a diverse set of people with different backgrounds. So the idea is to bridge the gaps and create a common language, hopefully. And we'll see how successful we are at that. So our first speaker is going to be Shinsei Ryu from Princeton University. And, well, you can see the title there. It's multi-wave functions, overlaps and applications, higher Berry phase, and multi-particle entanglement. So I'll tell you when there are 5 minutes left.
Okay. Yeah, thank you, Eduardo.
You can always ask questions. It's a lecture, so you can always, you're welcome to ask questions. You're encouraged to ask questions.
Yes, please. Okay. Thank you for the introduction, and then thank you for the kind invitations. This trip is my first trip to South Hemisphere, so I'm very excited. Like Eduardo said, I want to perhaps try to bridge between various perspectives, kind of like a field theory type perspectives, and then also the more condensed matter perspectives on the problem of quantum many-body physics. And then I changed my title a little bit to broaden the perspective. So I think initially the title was only about this higher Berry phase, but I also want to talk about something about quantum entanglement. So these 2 stories, I will proceed with the one theme, which is this multi-wave function overlap, and then that's what I'm going to talk about. This it's pointing, but it's a bit small, but that's okay. Okay. So yeah, like Eduardo said, please ask me any questions. Okay. So this is the plan. So I have a lot of time today, tomorrow, and then the day after tomorrow. Today I will mostly focus on some introduction part, and then 1+1 dimensions, and then I will also just talk about the lattice perspective, which is the tensor network type descriptions, and then in the later lectures, I will move forward to higher dimensional perspectives and also some field theory type approach to multi-wave function overlaps, and then I also talk about a quantum entanglement. Okay. So let me start with a very broad introduction. So I will start with just a regular wave function overlap. So that's basically inner product in quantum mechanics. That's a fundamental object in quantum mechanics. And then I may be using this diagrammatic descriptions where I use, okay, I'm not sure where it is pointing. Okay, here, yeah. So I may use this type of diagrammatic descriptions where I have an input state and output state, and then this gives you a number. That's a quantum mechanics inner product. I may be also using this type of description where I bend this part to upward. So in that case, you can think of this as the 2 states which are connected by this bond. So that is basically the quantum entanglement part, okay? In equation, this looks like this. I have a inner product, but it can be understood as a by using this maximally entangled state or Bell pair, and I just feed into two states into this bipartite Hilbert space. Okay, so that defines. So entanglement is a connection, and it defines the inner product. That's the basic idea. So the simplest example should be, of course, spins, spin 1/2, so it's a Bell pairs. Or we could do something more complicated, such as thermofield double state. Or, you know, there's a lot of interactions between quantum entanglement and then space-time. So you could also think of this as like a wormhole connecting two worlds. Okay. So idea is very simple. So multi-wave function overlap is multi-version of the story I just told you. So instead of considering the Bell pair, I could consider more complicated quantum state, which has a multipartite entanglement. as compared to the bipartite entanglement. In picture, it may be looking like this, or in equation, I want to consider multipartite Hilbert space. Here it's tripartite, and I have some state here. And once again, in terms of space-time picture, you may want to consider the space-time is many boundaries, like 3 boundaries, and then degrees of freedom lives on these boundaries, okay? Yeah, I'm losing point here and here, and then starting from these multipartite state as some sort of resource, we can also consider feeding in some state into these dangling bonds, IJK, or these boundaries. So we can think of this as the multi-version of inner product. So that is something I may call the multi-wave function overlap, or in this case, I may call it triple inner product. It's a 3-state version of the inner product. Okay? Okay. So the question is, can this be useful? That is my theme in my lectures. First, I need to define this more properly in the many-body quantum state context, and then I will illustrate this multi-wave function overlap is useful. Okay. I shouldn't. Okay. Thank you. Okay. Yeah, it's like kind of blinking. Is it? Okay. Thank you. Okay, I'm looking at you, so it's not a problem for me, but it may be annoying for you. Okay, so the idea is to define this multi-wave function overlap properly in the many-body physics context, and then we try to use multi-wave function overlap to describe something like a higher Berry phase. Just as a quick overview is that because of Berry, we know a wave function overlap is essential to define Berry's connection and the Berry phase and so on and so forth. And there's a natural question, if we define multi-version of the wave function overlap, there may be some phase or geometry or topology associated to that. So that is the first part of my talk. It's the higher Berry phase. And then, of course, we also saw the wave function overlap is closely tied to quantum entanglement. So we are going to discuss the multipartite entanglement in many-body physics context using various examples, mostly the topological states of matter in 2 dimensions. Okay, any questions? A question, yes. That's right. That's the. Yeah, I'm going to tell you. But like I said, idea is basically here. But in many-body physics, we have to properly define it. So we are going to define it. Yes. Questions? Okay. So let us now proceed. Okay. One more thing. So it is perhaps convenient to use this type of diagrams, network diagrams, to represent connectivity of the wave function overlap. So I may be using this language. So this is a regular in a product to state. Yeah. Okay, that's fine. It's a bit too hard to focus on. So yes, maybe I can stop here and then pause now, and then if you have any questions. Okay. Oh, okay. That's okay. Yeah. If I finish early, that's not a problem. Yeah. Yeah, that's a good question. Yeah, I'm not entirely sure. Maximal entangled state simply means if you put anything here, it will be automatically translated into this direction. I think it is related to the perspective to define inner product this way, but I'm not 100% sure. Yes. Other questions? Okay. Yeah, question? Mm-hmm. That's right. So yeah, so I'm going to represent, but this is not yet tensor network representations, but it's more like just a simplified version to just represent connectivity. So there's no notion of space in this diagram. But once we put, yeah, so now it's gone back. But yeah, the right lower corner right is the tensor network picture. I'm going to explain. Okay. But this is like a preview. So this one is the inner product. And I have 3 states. I have the tripartite state and 3 states. So let's say I, J, K, and then tensor product Hilbert space, A tensor, B tensor, C. And you can connect this way. I'm going to explain. So this is the triple inner product in picture. This is a more complicated version. This is quadruple version of the inner product. And then this one finally is related to more like the entanglement measure, which is called multi-entropy. And then that's like a preview of part 1, part 2, and part 3 of my talk. Okay. Once again, there's no notion of space. And then, but once I introduce space, it is going to look like more like the state defined on the one-dimensional line. And then there's a bipartition. But we could also consider 2-dimensional state, support it on the 2-dimensional plane, and we can tripartite this state. So we can go on now, or this is fixed, or still a bit blinking, but okay, maybe I can go on. Okay. Oh yeah, that's right. So the part 1, so this is now the 1 plus 1-dimensional quantum many-body systems, and I'm going to define a analog of Berry's phase, but as the title said, it's a higher form version of Berry phase. Okay, I think it's still blinking, but I think we can go. Yeah, it's still blinking. Yeah, I think I'll just go on, and then if they stop me, I will pause again, and then you can ask questions. Okay. Okay, so but let me start with the regular Berry phase. This is just a very well known, but it's good to review. So I have a setting as follows. I have a quantum mechanical state, but there's some adiabatic parameter you can change slowly. So I have a parameter dependent state psi, and then I have some sort of parameter space. And then each point in the parameter space, I have some wave function psi. X is a point on this parameter space M. Okay? And then essentially Berry's phase is the phase accumulated by the wave function as we adiabatically follow this path. Okay? You can also think of this as a kind of particle living on this parameter space M. But this particle trajectory couples to the current of this particle couples to this Berry's connection. So starting from this definition of Berry's phase. As I change my wave function smoothly in time, this is a phase, geometric part of the phase accumulated. And then you can also think of this as just a parameter derivative of the wave function, and then we take the overlap between 2 neighboring states in the parameter space. And then Berry's phase is essentially given by this, which couples to here dx dt that represent particles trajectory. Okay, I'm just slightly rewriting this way, which is not super essential, but just to introduce the notion of higher Berry phase. I thought it may be interesting to write this way. So it's like a particle current. So particle has a trajectory x of t, which is on this parameter space. And then for the particle trajectory, if you multiply the velocity of the particle, you can define the current. And then current couples to this fictitious U1 gauge field. This is not true electromagnetic field, but it's pretty much like regular electromagnetism. Okay, only difference is A is given by this Berry's connection. We also talk about a lot about topology, for example, in condensed matter physics. So Berry phase, Berry connection, and the associated curvature play very crucial role to study topological states of matter. So for example, from the Berry's connection, we can define Berry's curvature, and the integral of Berry curvature in parameter space is an integral multiple of 2 pi, okay? For example, M can be something like a sphere, okay? So that essentially measure the flux on M, and then flux on M is two-dimensional manifold M is quantized because of Dirac quantization condition. So in many condensed matter systems, for example, quantum Hall systems, and then Thouless pump, and something like that, this plays the role of topological invariant of quantum many-body state, or topological invariant of some adiabatic process, such as Thouless pumping. Okay, so this is important concepts. I'm going to first explain Wu Yan's perspective on this problem, and I'll try to generalize it to higher version. So Wu Yan's perspective on the problem of magnetic monopole is as follows. So we start with the parameterized state psi on parameter space M. But the point is that because of the magnetic monopole, you may not be able to take smooth gauge everywhere on the manifold to define quantum wave functions, okay? Because of the Dirac monopole, as it turns out, it is necessary to patch this parameter space, let's say using Ui, U beta, and then other patches, okay? And then that for each patch, you can define wave function smoothly using single gauge, but as you switch to different patch, you have to change the gauge, okay? For example, if I have a sphere, two-dimensional sphere, you may be able to patch by using the north pole patch and the south pole patch this way, and they overlap here, okay? The way to describe the charge of the Dirac monopole is to focus on the transition function connecting these gauges. So in this intersection of U alpha and U beta, these two gauges are related by the gauge transformation. I write it as E phi alpha beta. And then if there's a magnetic monopole inside this sphere, this phi necessarily has a winding around the equator. So the winding number of this transition function is the topological invariant of this U1 fiber bundle. And then it's counter charge of the monopole, Chan number. Okay, so that's a well-known thing. So I want to generalize this to higher version. So what I'm going to do, so this is here enters the concept of higher Berry phase. So in the context of many-body physics, it's been started around 2019, 2020. I have the series of works. I don't explain all of them, but I will try to explain the matrix product state or tensor network perspective of this idea of higher Berry phase. It's called higher because they have a higher form. For example, for the Berry's case, I have a one-form connection, one form, but higher Berry connection for the case of one-dimensional many-body state, it's a two-form connection. String theorists may call it B field. Okay, it's two-form connection. And then there's associated curvature, which is two-form for the regular case, and for the higher case, it's a three-form. Fundamental degrees of freedom, as we saw, it's a particle for the case of regular quantum mechanical system. There's a particle trajectory you can think of. But for higher Berry phase appears in the context of extended quantum systems such as string in the string theory context. But for us, quantum many-body system is an extended one-dimensional system. So that's why it can have a more interesting kind of very interesting, very generalized version of Berry phase. Okay. All right. So just I sketch the idea first. So just I repeat what I did for the case of regular Berry phase. So I had a particle here, which is parameterized by the adiabatic time t. But now I'm talking about extended state. Extended means I have now a notion of space. So I just call it sigma. So this is like a classical string, okay? And then, roughly speaking, I can consider the classical string wave function now, which is, once again, I'm using psi. And then I have a parameter space previously, but now I consider the string in the parameter space. And then string can sweep some region of this parameter space, and there could be some interesting question. Yes. Oh, yeah, sorry, Javier, yeah.
But a state always moves in a point like a in the Hilbert space. What is the physical meaning of a string?
Yeah, so you can think of psi is in the big Hilbert space. That's right. But it still depends, but it still depends on space. Does this make sense? So yeah, it's true that this still lives on the Hilbert space. That's true. But it's not like living in the many body state. Point in the Hilbert space. That's right, but I'm bringing in basically, so it's more like a continuous perspective I'm talking about here, but I'm bringing in local tensor product state structure in the Hilbert space. So it's a big Hilbert space, of course, but it has some local structures. So that's something we have to take into account now, right? Okay, so but this is first now just, sorry, I tried to describe, Worldsheet, yes, worldsheet, yes.
It's not supposed to mean in actual physical space. This is an internal space.
It's internal space, yes, that's precisely right, yes. Parameterized. So going back to Hilbert space structure, now there should be the tensor product space, Hilbert space for at each point sigma that we will be discussing soon. Okay. But now, at least formally, we can generalize the previous setting by introducing the string current by multiplying. So this is string trajectory. That is a delta function in parameter space, but I can introduce string current, and then there's something which couples to a two-form gauge field. Now, the current here is two-form. Okay. I'm not sure if I'm explaining this very well, but this is some basic idea. So if I have an extended quantum mechanical systems, we can have a higher form connection on the parameter space. Okay. And then idea is to not use this picture directly today, at least today, but I'm trying to consider lattice quantum many-body system, which is my string. And then I will try to formalize this idea of higher form connection. Okay, I hope it's clear. So let's move on. So the specific, very concrete setup I'm going to discuss today is the family, parameterized family of quantum many-body states, which is one dimension in one space dimensions, gapped. That is the setting. Okay, technically could also add invertible, which means there's always a single ground state, but in one dimension, that's not really the big issue. No topological order in one dimensions. Okay. Such a state, gapped short range entangled state in 1+1 dimensions, they are always very well approximated or very well described by a matrix product state. Okay. So I think many of you perhaps have heard about this tensor network formalism, but this is the formalism which allows you to write down the 1+1 the many-body quantum ground state using the product of tensors here. Okay, I think perhaps you're okay with this notation. So I have some tensor. These are so-called, so to speak, the physical legs, which represent physical degrees of freedom, spin 1/2. So this state can represent physical spin up or down. But additionally, there are these legs connecting neighboring tensors. These degrees of freedom are fictitious, or internal, which are separate from the physical degree of freedom, but nevertheless, they play a role to describe the entanglement structure of a quantum many-body state. I'm going to simplify this notation just by drawing this diagram without boxes to simplify notation. Yeah.
In one dimension, essentially any lab state can be approximated as a matrix product state with arbitrary accuracy.
Yes.
That is not true in higher dimensions.
Yes, yes. So that's why higher dimensional stories are more complicated. So I will start with one dimensions, and then in higher dimensions, there are more things we need to say. Like we have to limit my attention to the class of states, or I take certain quantum field theories or something like that. Yes, very good question. But 1D, it's mostly.
But I never understood what is the actual physical restriction that is made in higher dimensions by doing it.
Yeah, I think.
For instance, I have a number of gapless states like free-forming system.
That's right. Yes, that's how the very high entanglement. So there's of course, the consideration in terms of the entanglement scaling in one dimensions, area law or log violation of area law. In higher dimensions, it can be richer. And then also in higher dimensions, there's a distinction between chiral and the non-chiral states and so on and so forth. Okay, so yeah, it's certainly, I would say, more limited in high, or at least we have to be more careful in higher dimensions. Yes, other questions? Sorry? Invertible means single ground states on every manifold. So not topological order, essentially. But in one dimension, there's, okay, if you don't consider the gauge theory or something like that, there's no degeneracy. So if you have a tensor product Hilbert space, this is not really the restriction here. Other questions? Good, so let me move on. So I consider a family of matrix product states. So my tensor A depends on this state my tensor A depends on X. Okay, so this is the kind of analogy to previous slide, but now it's a bit more concrete. The tensors depend on the parameter X, which is living on parameter space M, okay? So the question is there a non-trivial family of such states? Like if I have a quantum mechanical state parameterized by parameter space S2, this family can be non-trivial if there is the non-zero Chan number, or if there's a monopole inside the sphere. Is there such thing? Is there any topological distinction between family of quantum many-body state? Okay, so the previous works I kind of broadly cited that there is such distinction, but in this case we have to use the higher version of Berry phase. Okay, so maybe I didn't explain notation very well, but for the case of Chan number and the regular Berry phase, it's the second cohomology group. Cohomology which distinguishes, it's an integer cohomology which distinguishes basically different Dirac monopole charges, but now we have to generalize it to higher form version. And then there's the two-form gauge connection, and then there may be three-form curvature. And then we are going to first study this family by using the Uyans type description, namely I patch my parameter space, and then for each patch, I have a very defined matrix product state in a smooth gauge, and so on and so forth. But what do we mean by smooth gauge in matrix product state? So that is the important point. Yes, question? I would say mostly the same. I think invertible may be a bit more have a maybe more rigorous meaning, I think, but many condensed matter physicists may say short-range entangled. That's the one popular terminology. And then long-range entangled may mean topologically ordered. So that means there may be a topological ground state degeneracy. But of course, if we try to speak something like a Berry phase, it's a simpler setting not to have ground state degeneracy. Okay. Okay. So that is the terminology comes from the fact that, for example, if you have you can always find the inverse of the state to cancel topological charge. If you have a Chan number, let's say n state, you can take Chan number minus n state, tensor product, the total Chan number cancel, which you cannot do for topologically ordered state, something like roughly 1/3 state. So that's why we can say invertible. That means you can cancel topological charge. For example, if you take the Laflin state, and then you can take you flip a magnetic field, and then you can take Laflin bar state, which has a 9 ground state degeneracy, which means it's still non-trivial. So you cannot invert Laflin state. Okay, I didn't invent this terminology, but as I understood, this is the motivation behind this terminology. Other questions? Yeah.
You want to mention short range and time that doesn't mean trivial.
That's right, exactly, yeah. That's right. So in fact, I'm going to discuss as an application of this to higher Berry phase to study SPT phase, and then so it's not trivial in that sense. It can be also non-trivial in the sense of family of state. Yes. Other questions? The degeneracy, yes.
By the way, people who are not organizers are encouraged to ask.
Okay, so I didn't, from here I cannot tell, but please ask any questions. Okay, all right, okay. So once again, it is important to clarify what is the gauge here. So let's first just look at the double intersection. So I have a parameter space, and I anticipate some obstruction to define single state, single MPS everywhere on the manifolds. I patch just to be careful. Okay, so then for each patch, I have a MPS representation which is smooth over this patch. But now the question is, when these two patches meet, what can happen? There's something called fundamental theorem in matrix product state, which says two matrix product state represent, so they can have different tensors, A alpha and A beta. They can have a different tensor, but nevertheless, they can still represent the same physical state only if they are related by this relation. So if A alpha and A beta, if they are related by conjugation up to some phase, so this part we don't care too much because this is just a regular phase redundancy of quantum mechanical state. This redundancy exists, or phase ambiguity exists even in quantum mechanical state. But new part is this G alpha beta, which is this part. Okay, so you can clearly see that if you insert this A into the previous picture here, all G and G delta they cancel pairwise, so they still represent the same physical state. Okay, so this is the gauge redundancy of the matrix product state, which is on top of the regular phase ambiguity. Okay, so I'm going to call this G alpha beta as a transition function or transition matrix in analogy to this E2 phi alpha beta, which is a transition function for the case of Dirac monopole. A question? The same, yes. I'm sorry, I said something like an inhomogeneous state, but now I'm considering just uniform translational invariant matrix product state in thermodynamic limit, which is perhaps not clear here on my presentation, but matrix product states formalism allows me to take thermodynamic quite easily. Okay, so I'm considering infinitely large matrix product state. Okay, so this is the question. Or no, okay. So this is the new gauge ambiguity which arises in quantum many-body systems. G's, yeah, so you have to fix some gauge, but after fixing this gauge, G is the unitary up to, it's called projective unitary because it appears in pairs. So there's still some ambiguity. But yeah, basically you can think of it as something unitary matrix up to some ambiguity. Okay. Now the interesting thing happens at triple intersections. If you consider 3 intersections, U alpha, so I have 3 patches, U alpha, U beta, U gamma. Their transition function connecting any pair of 2 patches, okay? And then G alpha beta is defined here, and then G beta gamma here, and so on and so forth. But there is also the triple intersection. And at the triple intersection, there are 3 different matrix product state representations for one physical state, okay? So let's do this exercise first for the regular quantum mechanics. So in the quantum mechanics case, if these 3 patches meet, there are 3 transition functions, 3 transition phases, okay? And then clearly you can see that they satisfy this something called the co-cycle conditions. This is because you can go from psi alpha to psi gamma in 2 different ways. So you start from U alpha, and then you transition to U beta. There's a phase here, but you can also go to U gamma patch starting from alpha via a second patch U beta. Okay, if I do this way, this is an indirect way. We accumulate this phase, but they should represent the same state. So therefore, they are related to this way. So this is a regular way. Nothing weird happens at the triple intersection. However, this is more interesting if I do this with a matrix product state. Okay. Okay, so now let's repeat this exercise for the matrix product state. So I go from patch alpha to gamma, and I do this in 2 different ways. So in direct way, I just go from a alpha to a gamma via this transition function, G alpha gamma. I'm omitting the trivial U1 phase part. But I could do this also by stopping over at U beta. In that case, I accumulate these two parts, G alpha beta, G beta, and G gamma, okay? But in this case, demanding consistency says G alpha beta, G beta gamma should be G alpha equal to G alpha gamma up to the U1 phase. Okay, so this is a new thing we are getting here, okay? That's because this always appears in pairs, of course. Okay, so sometimes we may call this the ambiguity of ambiguity because G alpha beta is already an ambiguity to represent for the matrix products the representations, but this C alpha beta appears in the ambiguity of G alpha beta. For the case of, once again, the Dirac monopole, I have a set of transition functions. I gave an example where transition functions is defined on the equator connecting 2 patches, south pole and the north pole patches, which can have a winding. Okay, so that defines the winding of this phase defines the second cohomology class, integer cohomology class, which is basically just the Chan number, so the charge of the monopole. Similar thing happens here. So I have a set of phases defined for each triple intersections. And using this data, you can construct the integer cohomology class, third cohomology class. Okay. So this is, as I understood, this one is called Chan class. And then for the third cohomology class, the topological class is called Dixmer-Dwadi class. So that is a topological invariant of the family of the state. Okay, so this is the the mathematical structure, but we are still lacking the wave function formula. Okay, so I will write down the formula to extract this phase. So the formula I'm referring to is this formula which extracts the transition functions. Maybe it was already before. So transition function, is given by the overlap between psi in the alpha patch and psi in the beta patch. From that, you can extract this phase. But is there such formula for the matrix product state? So this is how we use the multi-wave function overlap. Okay, so in order to extract this phase C alpha beta gamma, I now take a 3 matrix product state because I have a matrix product state at the triple intersection. So I have a 3 matrix product state representations. And then I consider the sort of overlap inner product for these 3 matrix product state. But now idea is to take the inner product or overlap between alpha and beta partially here, but the other part of this matrix product state is now connected to the other matrix product state, a gamma, and I do it in this way. Okay, so this is the idea of triple intersection. Okay, this is the in the previous definition I didn't have a space part, but this is now the definition of the triple intersection. Dot here means you have to take the complex conjugations. So in this description, we have to take half conjugation for the third matrix product state. Okay, so let's see how this can extract this G alpha beta, sorry, the C alpha beta gamma. That defines the topological invariant. A Dixon-Drudy class of the family of matrix product state. But let me just recall that how we compute a regular inner product in matrix product states. If I take the 2 matrix product state, we can consider the regular inner product. And then this type of regular inner product, we can use the transfer matrix technique to calculate. How do we do this? So this is the infinitely large matrix product state, but then we can define a transfer matrix here. This is the small piece of this inner product, and then multiplying this the transfer matrix, we can compute this inner product. I have a picture in the next slide here. So multiplying this transfer matrix many times, then essentially what survive in this infinite product of transfer matrix is the fixed point, which is the state with largest eigenvalues. And then there's the left and the right eigenvalues. So this expression here, which is a bit ambiguous at this point, because this is you should use the imagination that this is infinitely long, but something may be happening at the end, because there's a dangling bond. But the idea is that you can use the largest, the eigenvector corresponding to the largest eigenvalue of the tensor network to cap these 2 dangling bonds. So that defines the inner product here. Okay, I hope this is clear. So we are going to use this technique to evaluate this triple inner product. Once again, you should use the imagination that this part is infinitely long. But for each part, you can still use this transfer matrix technique. And if you use the transfer matrix technique, only thing that survives here and here is the largest eigenvectors or fixed point of this transfer matrix. So I cap off this network using this fixed point tensors. But then the rest can be just squashed. You can So you're asking, why do I have to make this part long? Yes. I'm interested in many body physics, in many body system in the large volume limit. Inner product is defined, but I want to, but yeah, it's a yeah. If you wish, this is a definition of inner product of 2 infinitely large systems, which may require some delicate considerations because it can be blow up or it can go to 0. So if you wish, this is how I define the product.
Is there any ambiguity or condition at this triple vertex?
This one here?
Okay, so you take the largest
Yes.
which for a single layer is
Yes.
defined.
That's right.
But there may be different ways of patching, gluing them together.
Yeah. So
There you just simply did a natural thing, which is to extend the line.
that's right.
But they can be twisted, and maybe.
Um,
I mean, for instance, this looks like a junction in some.
junction. Yes, it's precise. That's precisely a junction.
Sometimes put flux in these junctions.
That's right. So there are various interesting things that can be discussed. So in fact, there's some ambiguity how to cap off, but I guess you are mostly asking, can you put something here? That's right.
Is there something natural that you can put there?
Yeah, so that's an interesting thing we can discuss. We didn't do that, but so just a second, I'll just say one thing. And so in quantum field theory context, as I will explain later, this can be considered as a junction of three invertible lines which are meet here, so that we can resolve. So so there's many ways to resolve, but for the trivial topological lines, it does not matter. More interesting thing can happen if the lines have more interesting, maybe non-invertible or something like that. Okay. Sorry, maybe he asked questions first. Yeah.
Is there an ambiguity in the contraction and the connections between the three lines?
Yeah, that's what I was asking.
So yeah, that was the
It's the same question.
something may happen here. Yeah. So here we chose a particular way, definitely. But one can ask, is there something I can put here? Yeah, so once again, in this case, okay, so there's a microscopic consideration, the kind of universal consideration. So yes, microscopic level, you may want to put more tensors, but which requires more microscopic data. Perhaps we have to put new tensors or something like that. Yeah, so in the coarse-grained picture, yeah, so for example, I can put three topological line defect, and then it can be resolved some way. So there are some varieties, but topological lines, as far as they are topological lines, these configurations are equivalent. But it's a good, I don't say I completely giving a satisfactory answer. It's a good question if we should worry about the details here. But for this case, I'm convinced this is the correct way. So yeah. What? Yes, somebody told me this, and then it is closely related, and then I can talk about it, yeah. Question. These links you're talking about? Why you think it has to be even? That's okay. That's true. That's true. Yeah, but in this case, I think it's also possible to have 3 here and then 4 here and something like that. Yes, but I think that's okay. But separate question is, can we extract something useful for the finite length systems? Yeah, that I'm not completely sure. I think somebody asked me a similar question before. We are mostly working in a setting of infinitely large systems in thermodynamic limit, and then we can discuss what we can do with finite length systems. But then I think we have to really worry about how we terminate, because it's not unique termination for finite system. Here it's a unique termination because of this, something I didn't, because of a setting, this, you can show that this tensor here is unique in the thermodynamic limit. So that is, but for finite system, I don't know whatever tensor you can put, and you can just get different numbers, but there may be still something we can do with finite length tensors. Question? Sorry?
The leverage is of the thermodynamic limit is that is giving you a canonical coarse graining, and then at finite length you need another definition of coarse graining or not?
Yeah, I'm not sure if it is related to coarse graining, but it's certainly people do a lot of coarse graining in matrix product state to, for example, do RG using tensor network. But yeah, that's not related to coarse graining. I think there are two more questions here. Okay, maybe. That's a good, very good question. That's a kind of interesting but complicated detail I'm hiding here. So this formulation is much straightforward. If I take bond dimension to be constant for all patches, however, it is also known that for interesting examples, we cannot do that. So there's slight elaboration of this formalism, which I can also tell you later, but that's a very important point. So the short answer is, for interesting cases, no, you have to take care of this possibility as well, but we know how to handle it. Maybe one more question, or same question? Okay, good. So now idea, I think perhaps already evident, but I use this technique for each leg, and then I have this fixed point of the transfer matrices, and then by doing some simple calculation, you can see that this is equal to this number C alpha beta gamma. So this is the Uyan's generalization of Uyan's prescriptions to the parameterized matrix product state. Okay. Now I want to bridge this idea to field theory, in particular string theory, I guess. So after I found this triple in a product prescription, for some other reason, I was looking at my string field theory textbook, and then I found a very interesting similarity between string field theory, in particular this paper by Witten back in '85. So if you open this textbook, open this book, he describes his something called a cubic. Okay, sorry, I'm not entirely sure what is the proper name, but he's describing interaction vertex in string field theory. So in that prescription, 3 strings come, and then they interact. Okay, so that's the string field theory vertex. And then in his paper, he gave, so to speak, the non-commutative geometry descriptions. But anyway, details, I don't mean to explain everything. Perhaps some of the people in the audience may know much better than me. But if you just look at this picture, this is how strings interact. This is pretty much the same as what I had in the triple intersections. Okay? So I can even give very close connection with this open string field theory by reformulating the triple intersection a little bit like this. So I start from MPS, but now I have 2 MPS, and they first define the product, sort of a star product of these 2 matrix product state. Okay, so the idea is that I take I think of this matrix product state as a big matrix. So if I sort of split this MPS into 2 parts, on left and right, and I think of this is the low index of some matrix, and then I interpret this as a column index of some matrix. It's like a big matrix. If you wish, I can fold this to define operator like MPO. But then I fold them, and then, I fold this psi alpha, do the same thing for the psi beta, and they contract. So it may be looking like this. Okay? And then this part, by using the transfer matrix technique, I can once again shrink. Okay, so that defines another one-dimensional object where I have a psi alpha in the left part and the psi alpha on the right part. Okay? So this is a definition of the star product in matrix product state inspired by this paper. I could do the same thing. I could do an additional thing, which is integral, which is called integral. to define integral, I split this psi once again into left part and right part, and I fold like this, and then connect. So the resulting diagram looks like this, and then once again using the transfer matrix, this can be computed in terms of the left and right eigenvector of the transfer matrix. Okay? Now using the star product and then integral, the triple inner product, which I define here, can be understood as an integral of these three matrix product state. Okay, so this is the, I think, interesting analogy. We don't still have a full structure of the non-commutative geometry described by Witten, but at least the integral and the star product, I have a seems like a very similar or almost identical structure. Okay. Okay. So now I want to describe a bit about the simple case. I will have more examples later, but I want to describe a very simple example. So let's start with let's consider now the one-dimensional, 1 + 1 dimensional symmetry protected topological phases. And then I don't have an introduction here, but perhaps you may have heard about this. 10 minutes. Okay, thank you. Okay. So I have some on-site symmetry G, which protect the one-dimensional state, in this case MPS, being trivially connected, adiabatically connected to the trivial product state. So you can think of this case as a discrete version of the higher Berry phase. And in fact, we can extract the topological invariant of the SPT phase. Oh, 30 minutes. Okay, okay, good. I thought 30 minutes for questions, but okay. Okay, good, good. So famously, matrix product state gauge degrees of freedom plays a crucial role to describe topological classes of these SPT phases. And then it is the topological invariant is given by the second group cohomology, H2 of GU1. So can we extract this topological invariant? It is a bit like computing Chan number for regular quantum mechanical case. And then in this case, it's a many-body quantum state, and we are interested in extracting topological invariant. And then triple inner product can really do it. So idea is I start from the, let's say I start with the one given matrix product state, which is hypothetically representing the non-trivial symmetry protected topological phase. So we want to know if it is non-trivial or trivial, or what is this topological invariant in a second group cohomology. Okay, so this MPS is given in terms of some gauge. You know, it's some gauge. You write it down, so it is given in some gauge. In the symmetry protected topological phase, maybe I should go back to this. In symmetry protected topological phase, starting from some gauge, you can act with the symmetry of the SPT phase. But for the case of SPT phase, it is symmetry of the quantum state, so it should not change quantum state physically. However, the action here can be translated into the action in the virtual space. So acting with the on-site symmetry on some SPT ground state, you will change the gauge in the SPT, in the MPS matrix. So you do this for two different group elements in the symmetry here. So you get another state, psi G, after acting with symmetry G on this group G. But now that is physically equivalent, but now it's in a different MPS gauge. And you could do this with another group element H, which is also in this capital G. And then you take a triple inner product. Okay? And if you do that, as I said, this G can be translated into the inner action on the inner Hilbert space, represented by green, orange, and red. And then you can check that this triple inner product gives you the second group cohomology phase phi gh in the second, taking the value in the second group cohomology. Okay, this is a simple example. And then I will have more examples later, but this is one example. Okay. So far, I've been focusing on the equivalent of Wu Yan's description of Dirac monopole. So I have a patches, patch meet, and there's a transition functions. And then, so to speak, the winding or the non-triviality of this transition functions, or C alpha beta gamma, which I defined, that defines the topological invariant of the family of quantum state. But I can also take the point of view of Berry. Okay, so in that case, we just consider two states. These two states are on the same patch. I take a smooth gauge everywhere on a single patch, but I can take two neighboring states, psi at x and psi at x plus dx, and they take a regular overlap. From there, we can define a connection A, which is defined on some single patch, but I can also define curvature F, and the curvature is, you can define from a single patch, but then it is actually defined everywhere. Yes. Yeah. Of So I'm considering the it's an example of topological invariant extracted from triple inner product. That's right. So this is like a discrete case. So that's why I'm bringing more example later, which is perhaps more in this suitable for this context. But here it's like you can think of like a G as a discrete state, discrete space. It's not a continuous space, but like a G, H are the point on the group G. So that's the could be the Lie group, yes. But the Lie group. This is a discrete group. It's more like but the Lie group usually doesn't have a. I mean, Lie group doesn't have a two-core cycle. So, but that could be an example. Yes. Okay. Yeah. Maybe this is perhaps simple. I thought it's a simple example, but maybe it may not fit into the context of the talk. But this is a simplest example. Okay. Okay. So. Right, so now I'm switching to slightly different perspective, which is this varies perspective. So I take two adjacent states. So the natural thing to consider is the 3 points on the parameter space on a single patch, and they are very close to each other. And then can we define kind of connection? So far I did not speak about the connection, although I introduced the higher Berry phase as the higher version of Berry phase, and I said there's two-form connection, but I did not just introduce triple intersection. But I'm now going to explain the two-form connection, how this can arise from the tensor network. So once again, idea is I have a matrix product state, which depends on parameter, and then there's this ingredients such as transfer matrix, fixed points of transfer matrix. This is the right and the left fixed point. I should say that this idea was also studied in this paper, where they consider 3 points in the parameter space, which are very close to each other. And then they consider discretized version of two-form connection. This is a very natural thing to do. If I have time, I may come back to this formulation. But I already now present the equivalent of this Berry's one. So how we do this? So I think I'll just first show you the result. Okay. Yeah, maybe I should say there's a various formulation. For example, for this formulation, in this paper, they propose to use the Green's functions to write down the higher Berry phase. But this is the, we are going to present alternative prescription given in these two papers. So the formula for the two-form connection we came up with is this one. So it's a lot of fancy diagrams, but details are not so important. But just to describe the notation, remember I have these caps. They represent the left and the right fixed point of the matrix product state. And then these are, I take a derivative of these tensors, both A and then fix a point. And then this is infinitely long, this is the sum of the matrix product state with different lengths, but you can sum it. It's like summing ladder diagram, so you can write this way. This is the formula we found. And then I can say also this formula looks complicated, but so now here the idea coming coarse graining. If you are in fact in the matrix product state, which we may call fixed point matrix product states that appears after coarse graining many times, then certain things simplifies so that I can write down simpler formula here and here. And this is the formula for the very higher Berry curvature. Okay. Okay. So this idea is not directly connected to the triple intersection idea. I think it should be closely related, but we were not able to make a very precise connection. But we found this connection just by looking at the so to speak, the consistency conditions. So, sorry, I'm getting confused about which one advances, which ones go backward. Yeah. So this connection was constructed by looking at this structure of curvature, connection, and then the C alpha beta we discussed. So we have this following structure. So first of all, we have maybe we already discussed this part. So I have at the triple intersection, I have this C alpha beta, which is zero form, so I put 0. So collection of this data defines this Diximier-Doherty class, okay? But then there are a series of other objects, one form field, which is defined on the intersection, and then there's a two-form connection. This is a higher Berry connection defined on a single patch, and then taking the curvature of this Berry connection, now you define curvature, which is globally defined. So this is the hierarchy of objects or connections which we need to build, and then they are subject to these constraints. So this previous formula I demonstrated to you, we constructed such that they satisfy this series of relations. Okay, this looks of course complicated, but it is really the generalization of the regular U1 gauge field. So I have a two-form curvature globally on M. I have a one-form connection for each patch, and then when these two patches meet, there is a zero form, which is a transition function, which I wrote as a transition function, and it's related to these gauge fields. Sorry, this may be typo. So this is sort of, I transported here. So this may be typo. And then they satisfy this consistency condition I mentioned some time ago. But you can generalize this to this way. So this is really known in the math. But our task was to construct these objects such that they satisfy these series of relations. Okay? So that's something we were able to do. So in particular, in addition to this two-form connection, we also have to build a one-form connection on the intersection, and we found this expression, and these objects really satisfy these relations which are supposed to be obeyed. Okay? Yeah, okay. So now I will, the question for this. Yeah, maybe this is getting too complicated. I'm afraid. But anyway, this is what we did. So now let's move on to the example, okay? So the canonical example of this type of physics we're discussing is very similar to something called Thouless pumping in condensed matter physics, which is, Thouless pumping is the non-interacting one-dimensional system where you change the parameters in the chain adiabatically, and then it transports the quantized charge from the left of the chain to the right end of the chain. So that is known as the Thouless pump. It is characterized by the Chan number in the parameter space, and it was even experimentally realized and observed. Okay. This is a generalized version, but it's an interacting quantum spin chain. Okay? Okay. So it is described here as by a picture and also Hamiltonian, but you can focus on the picture. So I start from the, this is spin 1/2 chain. In this process, it's initially dimerized, okay? And then this parameter W1, vector W, and the three-component vector W, and then W4 is the parameter. I'm only changing W4, but it starts from the dimerized chain, and then in this time period, I also changed the on-site Zeeman field, which is given by this vector W. And then at some point, we switch off this dimer, but now we connect the neighboring spin in a different way, and then we continue, okay? So if you know the non-interacting version of the Thouless pump, this is somewhat similar, but we are doing in the many-body setting, okay? Yes, we have, we transport. There's a sense that this part adiabatically moved to this point. That's right. So it's a product of singlets. That's right. Yeah. And then this Hamiltonian looks complicated, but this is just explaining this picture. Okay. And then if we apply our two-form connection to this problem, so this is an example where we can compute matrix product state. We can construct matrix product state analytically for these for different parameters, and then we can go ahead and calculate our formula for the two-form connection. So I'm not explaining maybe this part very well, but W4 is cosine t, and cosine theta is related to this three-component vector W. I forgot which one, but it's just a regular radial coordinate. And if you compute, you can actually get this two-form connection. And then important point is that you can show that it is actually quantized as expected. So our formula is really working. Okay. So this is the kind of check we did, and it seems it's working nicely. But I also want to show you kind of numerical work, which is nice because it's a very down to earth, and it can be done for other examples. This is kind of analytically tractable example, but we can do this for other examples, and then that will be very nice. So, so this group from Harvard, they also did the equivalent thing for the two-form connections. They have an identical formula, but they can compute this even numerically. And then you can show that as they change the adiabatic parameter alpha, I think this parameter corresponds to W4. Then this higher Berry curvature eventually, as you integrate, it's actually show the quantized value as expected in these numbers. and then these are different values of bonds. So I think for some bonds, for analytical calculation, you cannot change, but numerical, you can do other things. So this is how things change. But it's another check, and then this is now the even numerically implementable. This is slightly different thing, which was done a bit earlier. So this is like a discrete version of the formulation where they chose 3 neighboring points, but they really didn't take the limit where these 3 points coincide. So they don't take the derivative, but they just make this each triangle smooth enough. Okay, this is like a lattice gauge theory version of the higher-vary connection. But they can also demonstrate that their discretized version also gives you the quantized topological invariant. So we can now compute this higher-vary connection curvature and the associated topological invariant numerically, like using DMRG, for parameterized family of the matrix product state. So this is basically the end of my first part. It's all about one-dimensional matrix product state. I can move forward a little bit with part 2, but I think it may be actually good to stop here. It may be a bit too early, but yeah.
Suppose instead of doing the thousand span, you look at something like the Condensed state or the ICTP state, which is spin 1.
That's right. Spin 1.
Spin a half is a two-dimensional Hilbert space.
That's right. That's right.
Okay, so it's non-trivial in that case. So it's an SPT. Essentially, is that the same way? How do you deal with that? Because the two states that are sitting at the endpoints.
That's right.
They are entangled.
Yeah, that's a good question. Still invertible state, and I can write an injective MPS. I should be able to do what I said, but yeah, but physically I should have a singlet which has the degenerative.
It's a singlet with the other guy at the end of the universe. Okay?
That's true. That's true. But
Looks like a two-dimensional Hilbert space.
that's right. That's right. Good question. We haven't looked at that case.
What sense is that invertible? That's what I'm trying to understand. And what's the topological invariant?
That's a topological invariant. So yeah, so certainly if I think of this as an SPT example, I should be able to still do the example I mentioned. But you can also consider deforming it and then singlet evolves somehow. Yeah, I haven't thought about that case, but that's maybe another interesting case we can study. Okay. Question? Yeah, it's a family of state. Family of state. So it can be considered as the ground state of the family of Hamiltonian, where gap always stay open. Or but you can also just consider parameterized matrix product state. But yeah, it's usually convenient to consider parent Hamiltonian, which has a gap. Okay, another question? Yes. Mm-hmm. Yes. Uh-huh. I see. So yeah, maybe we can approach axiomatically. So I'm not entirely sure which axiom we should have, but perhaps we can, like a positivity and so on and so forth, maybe continuity and so on and so forth. We have not approached axiomatically, but That's right. That's right. Yeah. So I would I wouldn't think axiomatizing this way, but I'm very interested in, for example, axiomatizing using the axiom of non-commutative geometry. And then this is nearly as complete. For the non-commutative geometry, I need one more axiom to satisfy, which is the Z2 grading. So that we don't find how to formulate it yet. But for example, if I find this Z2 grading BRST charge, whatever, then this fits into the axiom of non-commutative geometry. So that's mathematical descriptions, but there could be other mathematical formulations, certainly. Question? Yes.
So in the end, the product state of the three states, the one that you were, the inner product of the three supertypes, was dominated by the high eigenvalues of the transfer matrix, right?
Yes.
So is there a way to think of this as a consistency relation in the scattering problem, like? Because it looks like everything is controlled by the infrared states, right?
Right.
Is it somehow related to the idea of a consistency relation?
So I don't know enough about consistency of scattering, but consistency of S matrix. Yeah. We have not thought that way, but maybe it is perhaps possible to formulate everything using asymptotic state in and out state, and then something. I think there's maybe another way to. I'm not sure it's the same, but you can think of the. I'm not sure. I think the problem may be that I need somehow. I'm not sure. My impression is that I need a time which branches. So I need branching time or two time or something like that. But maybe it's interesting to think about. Yeah. Eckermann? Yes.
It's like a fusion beam, on the other hand. You're fusing.
Yes. So I can tell you a bit more about field theory interpretation, but yes, you can think of this in terms of fusion, or OPU or something like that. Question. That's right. That's what I'm talking about. I'd love to construct that. So that is something we are still missing. So if I have a Q, this is complete non-commutative geometry. Yes. Yes, John. Yes. So that's related to perhaps Eduardo's comment and questions. I think it's related to something we are seeing here. There's some sense that something is transported to here. But this is, in this picture, it looks very similar to Saurus pumping, but I think it should be higher version of Saurus pumping, and people usually say it's the flow of very, I think usually they say this is phrased as the flow of very curvature, but I don't know enough about it. It's not a very curvature itself, but it's like a very curvature is transported. But I don't know enough about it. So, but that's something. There's some sense that something is transported from left to right. Jen? Yes. Okay. This famous big book, which can be downloadable from the web, and then. Oh, okay. Maybe you should tell me about this book. Yes. Question. Yes. That's right. So sorry, I didn't explain this very well. So W4 is parameterized by T. And I have a 3-component Zeeman field, which is, I'm using the radial coordinate phi and theta. So that's why it's sitting theta and phi here. Yeah, sorry, I didn't. That's right. So altogether, they have like a 4-component vector, but it is really parameterizing the S3. Yeah, thank you for the question. Yeah. Another question? Yes? Yes. So this is just trying to describe, we are changing also the direction of the Zeeman field turning on. So here I focus is more on the connectivity of the bond, but I'm also doing something for each side. So yeah, maybe I didn't once again explain this model super well, but there's a alternating field. So that's why something I'm turning on here, so that the plus and the minus. If it is plus on this side, next one has a minus because of this alternating sign. That's another part of the time evolution. Yes, question? Yes. So we are. Yes, very good question. We are working on that. So there's a known connection between two form and the higher form curvatures using the concept of loop space, but that we have to deal with inhomogeneous state. Then we can formulate it. You can sort of see that this inner product maybe it's not obvious from here, but basically you can translate this into the inner product of inhomogeneous state. But in that case, we don't need a triple inner product. But that's we are we can talk more about it. Yeah. Paul, yes. Yes, so jar is this something called higher structure, and then okay, so it is really this. Oh yeah, I'm going. Going the other way. So yeah, sorry. So maybe I didn't mention this is the whole thing is fit into the something or job structure. So maybe the appropriate slide is okay. I'm not sure. Job appear later. Yeah, but let me first stop here. So. Okay, maybe it's actually go to the like you said. So this is something called abelian. Okay, maybe advancing backward. This hierarchy of the structure I presented here. It's known as the abelian gerb, and then usually. Okay, so I'm not sure. I'm not the right person to explain all these things, but. So in gerb, this intersection, you define the basically complex line bundle, U1 gauge field. So that's why we have I have transition point. So that's like a more complicated version of this, where I have a at the intersection, I just have a U1 phase here, but instead of putting U1 phase here, you put the complex line bundle on the intersection, and then there's the consistency at the higher intersection level. I'm not sure this is the correct or best way to describe it. You can also define gerb without using these connections, which we also did. maybe I can explain that better later. But yeah, that the whole thing is called the gerb, and then this is really considered as a something like ambiguity of ambiguity, where in this case ambiguity up to this point, but there's no ambiguity at the higher level. But in this case, you go to the ambiguity which persists up to higher intersections, and then there's the ambiguity, for example, is described by the intersection at U of two patches, which is ambiguous, still defined by the a complex line bundle and so on and so forth. Sorry, maybe I didn't do a very good job, but this is something called the gerb. Yeah, good point to start. Yeah. Thank you for your attention.